Okay, so welcome everyone to the welcome everyone to the first talk of this session. In fact, the first session before the closing remarks, and so we are very happy to have Bharat as our speaker today. Bharat Adsul is a faculty member in the computer science department at IIT Bombay, and Bharat did his PhD also from IIT Bombay itself, and then he was a faculty member at CMI for a few years. So Bharat's research interests are primarily in formal methods, particularly in the area of concurrency, like automata logic games, and he also works in geometric complexity theory as well as mathematical program. So today he is going to talk about games played on asynchronous transition systems. So over to you, Bharat. Thanks.
Am I audible? Yeah, it's working, right? Yeah. Okay, so let me start by thanking the organizers for this wonderful meeting and for the kind invitation. I'm going to talk about games on these asynchronous transition systems. And this is joint work with Nehal Jain, who is also there in the audience. So if I cannot answer your questions, you know whom to ask. Okay, so let me begin and let me sort of say few words about the motivation for studying these games. So the motivation comes from this problem of distributed synthesis. Okay, so so reactive synthesis is about the following sort of task. You are given a specification. The specification, in some sense, asks as to what the system should be doing, right? It has this sort of information about what is in the control of the environment, what is in the control of the system, and how do you want the system to react to the environment. That's what the specification, in some sense, talks about. And given this specification, you want to synthesize a system which meets this specification, right? So no matter how the environment behaves, the system responds in a particular fashion so that the specification is met, right? That's what the reactive synthesis is all about. It's of course a very active research area, and yeah, but the focus of this talk and the motivation for this work is this distributed synthesis problem, where you are given a distributed specification. So, so the specification is distributed. There is some information about the underlying architecture, right? The underlying distributed architecture, or we want to synthesize a distributed protocol, let's say. So I'll use these words program, protocol, system interchangeably. Okay. So given a distributed specification, synthesize a distributed protocol that meets this specification, right? So think of the mutual exclusion protocol for two processes, right? And all of us have seen this wonderful algorithm due to Peterson's, right? Which sort of solves this mutual exclusion, has these right properties, the right mutual exclusion properties, right? And the question is, can we synthesize some such protocols automatically? Can there be a tool which will take this specification and synthesize the protocol which meets this specification, right? Respecting the distributedness of the requirement. So of course this work has a long history. So it was sort of the first model was proposed by Noeli and Rosner in 1990. So there have been various models, and one of the key difficulties in this area has been identifying sort of a right model, in the sense a model which is fairly expressive and which gives some good decidability results. Okay, so in the distributed setting, the mechanism by which the processes come to know about each other's information, right? The communication plays a very important role, and then different models look at different forms of communication mechanisms. There can be a message passing mechanism, or there can be a mechanism where the processes learn about each other's state through shared variables and things like that. So the starting model was by Noeli and Rosner. I will not say much, and there has been, of course, later work. But the earlier model was quickly shown to be, in the same work, it was shown to be undecidable for very simple sort of beyond very simple architectures like pipeline architectures. Yeah, and there has been, of course, later work. But in the last 10 years or so, in the last decade, these two models got very popular and have been extensively studied. So these are Petri games and asynchronous control games. So let me not sort of say more about these things. I'm going to talk about a model which is very close to this model, asynchronous control game. So maybe at some later point, I'll make a comment about how our model compares with this. And these models, we have several interesting results in these newer models, unlike the old Noeli-Rosner model. But again, 2-3 years back, it was sort of the bad news hit us again, and then these models are also now shown to be undecided. Okay, so this is just some motivation, but don't worry if you did not understand any of this, because this is just, this is just the motivational part. Okay, but so before we actually talk about these distributed models, let's go back to the origin of reactive synthesis, the sequential synthesis. And this goes back to the following sort of very influential problem due to Alonzo Church. Okay, so-called Church's synthesis problem. Okay, so way back in 1957, Alonzo Church asked this very wonderful question. Okay, so what is the setting? The setting is that you have these two kinds of letters, input letters and output letters. Okay, so we have these input letters and these output letters. And you have a specification which is talking about properties of an infinite sequence of input-output pairs. Okay, so that's what the specification says. So essentially, it's kind of saying that, for this infinite sequence of input, this infinite sequence of output letters is fine. We'll look at some examples. So there is a specification which kind of couples the input and output. And what Church asked is whether, asked us to design a program or a circuit which realizes this specification. Okay, so let me make some of these things clear. Okay, so what is this circuit supposed to do? So the circuit that we want to design should have the following property. So imagine that there is a global clock which is ticking. Okay, so at the first tick, an input letter is provided. Let's say it's one of these letters, input letter is provided. Let's say that's I1. What this circuit should do is that it should look at this letter I1 and it should output an output letter. It should sort of produce an output letter. So let's say that is O1. Okay. At the second time, the second time tick, the second input letter arrives, I2. And the circuit has to now output the second output letter, right? So it's a circuit which is sort of, getting this infinite sequence of input letters, right? And as soon as an input letter arrives, it has to immediately produce an output letter, right? Yes. So this is at time one, so this is one particular sort of input, right? So think of this I1, I2, I3, I4 as a particular single input sequence which is provided to the circuit. And as the circuit reads this, right, it starts producing the output sequence O1, O2, O3, and so on. So C is computing this function in some sense. C is the transformation which is transforming an infinite length input sequence into an infinite length output sequence, right? At every time, it's kind of producing one letter of the output, right? Yeah, so I'll come, you can think of it like this, or let's look at I have some small examples which will make all of this clear, right? So the main requirement of the circuit is that output has to be produced letter by letter in response to an input letter, right? And the output which is produced at time instance n, which is O(n), right, is allowed to depend only on the past input sequence that the circuit has seen so far, I1, I2 up to n, right? This should happen for all n, right? So at every time instance, the output letter that is produced depends only on the input letters which the circuit has seen until that point in time, right? So this should happen, and this property should be satisfied. We are saying that this circuit realizes the specification phi. What? No. It's equally a property of a pair of, so essentially think of it as a infinite word over this input cross output alphabet. So look at the cross product alphabet and I have infinite sequence over this, right? And the specification is saying these are good sequences and these are bad sequences. You have an example, right? It's not just one particular sequence, right? So yeah, it's a subset of, all infinite words over the alphabet I cross, input cross output alphabet. Yeah. But that's okay, right? Because the same circuit is computing it, the same circuit can store O1, and then with additional storage, you can kind of, in some sense, it's hidden, right? It's you wait. The second is the requirement of the circuit, yes. Not on the fee, right? The first two are completely requirements on the circuit, right? The circuit has to sort of work at every clock tick. The first two are requirements on the circuit. The third thing says that no matter which infinite input sequence is given to this circuit, right, the output infinite sequence that the circuit produces, right? So for all infinite input sequences, I1, I2, I3, blah, 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 right? The outputs which is produced by this circuit, which is O1, O2, O3 at these time sticks, right? If you look at this input-output sequence, infinite input-output sequence, I1, O1, I2, O2, that should satisfy the property phi.
So, sorry, how is the specification given? Like it's
Yeah, I'll come to that. Sorry. Okay. So yeah, maybe so it's not quite clear that such a circuit always exists, right? So for instance, let's look at this simple let's look at this specification. So my input alphabet has these three letters, right? A, B, C, and the output alphabets are 1, 2, 3, right? So at every point, one of these letters is going to come as an input, right? The circuit that I want to design, it is going to see one of these letters as an input, and it has to produce one of these three numbers, 1, 2, 3. That's the output letter, right? The circuit consumes a input letter and produces a number between 1, 2, 3, right? And suppose my specification says that I want this property to be maintained, that the first output letter that I generate is 1, if and only if in this infinite input that I'm going to see, the letter B occurs infinitely often. Right. So essentially what I'm doing that at time instance 1 itself, I must produce the output letter 1, right? And that should happen if and only if in the overall input, the letter B occurs infinitely often. Okay, so it is not realizable, right? No. So the specifications, the good sequences are these, where the B occurs infinitely often in the input part, if and only if the first output bit is, the output letter is 1. Right. So those are the good sequences, and you cannot design a circuit which will always guarantee that no matter what input comes, you'll always produce output right within this set. Right, because at the time you have to produce the first letter, all information you have is the first input letter is all that you have seen. You don't know what's going to come in the future, right? So no matter what you do, the input letters, right, the input sequence can be modified later so that your circuit is wrong, right? So it's clearly that not every specification is realizable, right? So, so of course, there is a, right? So what the synthesis problem is, given a specification phi, first of all, decide, right, whether there exists a circuit, right, which realizes this specification, right, and realizes in these three senses, right? So whether there, yeah. That's true. In this case, that's true. Yeah. But you could, the point I'm talking about is the specification language allows you to talk about, infinitely many occurrences of certain things. It certainly allows you to do some threshold counting and things like that. Right? The specification is rich enough. Yeah. And over finite sets, right? So so that is really sort of one very interesting feature of Church's problem. The data is kind of finite in some sense, but the infinity is at the time axis, right? Because you have to maintain this interaction for infinite amount of time, and at infinity you want to meet the specification. So the infinity has gone from the data side to the time side, if you want, right? And that's kind of makes the problem challenging, right? So it's not, it's not quite clear how to sort of decide whether a given specification is realizable, right? And so let's look at another interesting example. Okay, so the same setup. Yeah. Yes, yeah. So correct. So I'm going to so I don't want to spend much time, but we are going to restrict to see linear temporal logic specifications or monadic second order logic formulas. But we are going to essentially work with these combinatorial kind of conditions. Specification is going to be this combinatorial in nature. So let's look at this particular example. Yeah, at this point, yes, but it was, yes. Right. I mean, first of all, even if the specification is realizable, it's not clear, what kind of program will realize it, right? So there is, so. Okay, but let's, Right? So let's look at this specification. So the specification, so again, we are in this old setup. So the input letters are ABC and the output letters are 1, 2, 3. Okay. And the specification says that for the circuit to behave correctly or to realize this specification, what must happen is that the highest number which occurs infinitely often. So output sequence is a sequence of numbers, right? So look at which numbers occur infinitely often. Look at the one which occurs, which is the highest among these. Okay, so the highest number which occurs infinitely often on the output part should match the number of letters which occur infinitely often in the input part. Okay. So for instance, if you look at this sort of input-output behavior, A comes and the output is 2, B comes, output is 2, C 3, blah, blah, blah. And then at this point, B and the output is 1, A output is 2, and this repeats omega times. This behavior repeats, right? So if I have a sequence like this, then you see that the letters A and B occur infinitely often on the input side, right? The letter C occurs only finitely often because after this, right, after this point only letters A and B occur. So two letters occur infinitely often, A and B. And if you look at the highest number which occurs infinitely often, it's 1 and 2 are the two numbers which are occurring infinitely often. So the highest number occurring infinitely often is also 2, right? So this particular computation is kind of good with respect to phi. Phi will sort of say, okay, this computation satisfies phi, right? So along this computation, this property is maintained, that the highest number which is occurring infinitely often matches the number of letters which occur infinitely often, right? And the question is this realizable? Is this specification realizable, right? And it's, any guesses? Yes. How do you realize it? Something like that, yes. Okay, so yeah, that's right. Okay, so here is a program which will do it. This is the English description of the program. So whenever the circuit gets to see this letter I in the input, okay, which is one of these letters A, B, C, right? So whenever the input letter I comes, what the program does is it outputs that number which corresponds to, how many different letters have occurred since the last time I saw the letter I, right? So you are seeing a sequence of letters, right? At this point, I'm seeing a particular letter. I see, when did I see this letter last in my past? Because I have access to the past, right? The circuit has access to what all inputs came in the past. So it looks at the last occurrence of the same letter, and since then, how many letters have come, right? If that number is, whatever that number is, the circuit just decides to output that number, right? So for instance, here is what the output would be. So A comes, it says, okay, I'm seeing only one letter. B comes, last time I have not seen B, but I see an B since the last B was at minus infinity, say. So I output 2, at C I say 3, and so on and so forth. Then if you see B and A, right, you say this is the B, right? The last occurrence of B was here, so I output 2 because I saw seen B and A, right, since the last. And on A also I output 2 because since the last day I have also seen a B. Right, so for the same input, this is how the circuit will sort of behave, and it will actually meet the specification, right, on this example, right? But in general, you can sort of convince yourself that this program will realize this specification, right? So it's not quite immediate, right? Given a specification, how to decide whether it's realizable or not. And somewhat surprisingly, this was sort of shown by these two people, Buki and Landweber, and sort of 1969, quite soon, I would say. Okay, so what they showed is that this Church's synthesis problem of realizability is sort of decidable. Okay, and yeah, here is where I want to say a few words about what the specification is. So the specification is either S1S formula or MSO logic formula or LTL formula, those kind of formalisms, and all these properties can be easily expressed in those formalisms. The properties that I gave as examples, okay, they can be very easily coded inside these specification languages. Okay, and furthermore, Buki and Landweber actually proved this very exciting sort of result, that they said that whenever the specification is realizable, right, not only it's kind of realizable, it can be realized by a finite state program. Okay, so the circuit in some sense has only finite amount of memory, right, where it is storing some key information about what has happened in the past. And based on that key information, it is going to sort of spit out the output letters, right, in response to the input letters as it sees. Okay, so it's kind of, okay, so yeah, so there is always this guarantee of a finite state program which realizes the specification, provided if it's an yes instance of. What are M and N? Oh, yeah, it really heavily depends on the specification. So if you are looking at these kind of specification languages, which is what I think Buki and Weber looked at, it is non-elementary. So it is highly impractical. But if you go to LTL, then I think it becomes, I don't, maybe it's doubly exponential or something like that, or maybe triply exponential. I'm not sure, but it's certainly elementary. Yeah, if you, you could think of it an automata as just a circuit, right? A combinatorial circuit where it has, you have some registers where you keep the memory. That's the language that Church was probably talking about. But yeah, you could think of automata. That's where I'm going to switch to. There is no infinite ever. The infinity is the input is coming, it's an infinite sequence, but it's coming letter by letter. Yeah. So the amount, yeah, by finite state, I mean essentially an automata. Exactly. No. It was his S1S was what he was, what he was focusing on. He sort of posed this problem and he said, in particular for S1S, can we solve this? So second order theory of first successor, this basically it's an omega-like structure, natural numbers and the successor relation. Yes, that's why it's monadic synchrology, right? You are allowed to, so you are kind of, what is the subset of positions where something happens and things like that. Yeah. So you allow, you go beyond first order logic, but to the limited signature where you are plus and less than and things like that. Yeah. Okay, so so it's not sort of very hard to see that this Church's synthesis problem can be easily visualized as a game. Okay, so let me just do that. So let's look at this earlier example where there are 3 input letters and 3 output letters. So I just create this sort of very sort of trivial NFA, right? The 3 states of the NFA corresponds to the 3 output letters, 1, 2, 3, right? And I have these non-deterministic transitions. In fact, from every state, I am allowed to read one of the input letters and go to any other state. So it's right from anywhere you can go to anywhere. The states correspond to the output letters, and the sort of the transitions are on input letters. Okay, so this is a NFA. And then I think of this kind of interaction between these 2 players called environment and system. Okay, so there is a sort of given start state. So imagine that there is a token which resides at the start state, right? And now environment chooses an input letter, right? And the system, chooses a target state on that input letter. Okay, so in the Church's synthesis problem, the environment or the input was coming from somewhere, from the sort of environment, right? From external, it was externally provided, and the circuit was outputting, was responding to it by producing an output letter. So we are essentially simulating the same thing, right? So the environment chooses an input letter. So suppose I am here and first letter is A, so the environment says, okay, I want to do an A. And depending on what the output letter is, to that A, I can respond by, if I want to output 1, I'll just use this transition and stay here. For that, on that A, if I want to output 2, I will move here. Right? If I want on that same A, I will move here. So I have these options of, giving whichever output letter I want to provide. And that is modeled by these 3 target states, right? So you can just think of a very sort of naive game, right? Where the point is the environment chooses the letters and the system chooses the transitions on the letters, right? So there is a non-determinism in the transition system, and the non-determinism is resolved by the system, right? The environment produces the letter and the non-determinism is resolved by the system on that letter, right? In this game, I am allowing non-determinism. Because you could play any letter, right? The input letter, right? At the first instance, I could play any of the letters, right? No matter what input was given, the circuit is supposed to work correctly. So at the first time tick, I could play A or B or C, right? And the output is up to you, right? 1, 2, 3. So here the output is kind of modeled by the choice of the system. That will become a problem of deciding whether this game has a strategy or not. So in the strategy part, the choice of output will get fixed. Exactly, right. So producing the output in the churches in this problem will correspond to producing matching transitions in this game by the system player, right? Yeah. So the plays, a play of this game essentially can be thought of as an infinite run of this machine, right? Where the input is provided, the input sequence, right? Infinite input sequence is provided by the environment. And the run is provided by the system, right? Because it is sort of saying, go here, and use the transitions to match this input, right? So a play is nothing but an infinite run of this from this initial state, right? And the system wins this run if the corresponding sequence is basically infinite, input-output sequence satisfies the specification. So the winning condition is kind of captured by the specification, right? And sort of, just reformulating Church's problem, now it will mean that a specification fee is realizable if and only if there exists a strategy for the system player to win this game, right? To ensure that no matter what happens, no matter what input is presented, the specification fee is always satisfied. It's allowed, right? It's able to move the tokens along the transitions so that the specification fee is always satisfied, right? No matter what inputs are provided by the environment. This is just a reformulation. So yeah. So it is not, yeah. No, that is gone. Yeah, and then of course there is a lot of sort of stuff hidden in the specification fee. I have not simplified that, okay? And I'm going to actually skip that part because that is where the sort of, serious advances in automata theory are used, okay? So the way we sort of see, this Church's Landweber theorem today is that in some sense, you have this input-output behavior, right, which the specification is talking about. And what we can do, thanks to these results in automata theory, is you can essentially have a deterministic referee, right, which gets to see this input-output, infinite sequence, and it decides whether the input-output sequence satisfies phi or not, just based on whether this this sequence is accepted by the automaton or not. So the logical condition of satisfying P basically turns into an automata theoretic acceptance condition, which is completely state-based. Okay, so there is a lot of sort of machinery which goes into that, right? But the point is that, one can take that referee automaton and take essentially a cross product of the referee automaton, whose job is to check phi through a state-based condition with this trivial sort of, game structure that I have, right? Input-output game structure, and build a new automaton, a new game structure, which is now who's sort of where there are these non-trivial states now, right? And then inside the states is also encoded what output I'm going to produce when I come to that state. So I'm saying these automata theoretic results allow you to convert this problem, which has this logical component of specification, into a purely combinatorial game problem, right, where the game is played on an automaton. Okay, so I'm going to sort of not talk about that part, but so this is the main point. Okay, so we are back to this sort of old situation where the environment chooses the letter, the system chooses the transition, but now the system job is to sort of produce transitions in such a way that, the infinite path that is traced, right, inside this structure now has to satisfy the state-based winning condition. Okay, so the notion of winning now just refers to which states occurred along this infinite computation, right? And which states occurred infinitely often, which states occurred at all, and things like that. Okay, so from a logical sort of specification, we have gone to a state-based winning condition at the level of the automaton. Okay, so that's what. Yes, there are omega regular and there are deterministic automatons. Exactly. Okay, I'm kind of going rather slow, but okay, so let's look at a game of this form. So let's look at a safety game which is played on an automaton, right? Played on a transit system. So here is, so you have this automaton, right? An NFA, really, right? And suppose you start at this state S1, right? And in this case, this state S3 has been sort of declared as an unsafe state. Okay, so I have essentially a NFA, right? A designated start state, and then some states are declared as unsafe, right? So in this case, S3 is an unsafe state, right? So how does one play this game? So you start at S1, right? And at S1, right, currently, if you see, there are two letters which are possible, B and C. The environment selects a letter and the system just responds by a matching transition on that letter. Okay, so let's say at S1, environment decided to pick a B, and the system had these two options, either go to S2 or S3, and it decided to go to S2. Okay, so this single edge corresponds to two things, right? The environment chose B, and the system chose this transition on B, right? So this is sort of one instance, one round of interaction between the environment, right? And then at S2, let's say the environment chose B, and then the system decided to take it to S4, right? And then at S4, environment chose B, the system decided to loop here. And let's say this is what happens forever beyond this point, right? So now if I look at this particular run, right, this unsafe global state does not occur, unsafe state does not occur along this run, right? And therefore you will say that the system has won this particular play of this game. Okay, so system will lose a play. This is a winning play, but system will lose a play if the play has gone through an unsafe state at some point, right? If someone's right. So for instance, that could happen if after, after sort of staying here for finitely many times, if the environment schedules a C, right, then there is only this option on C, and then that will lead to a losing play for the system, right? Yeah. So now, given this safety game, right, you want to decide, whether there is a strategy for the system to ensure that the token always remains inside the safe set, right? So, okay, and this can be very easily sort of solved by a simple fixed point computation. Okay, so let's look at that. So essentially, the idea is the following. What you want to do is that you want to compute this part of the state space that's called Xi. Okay, Xi is those states, right, from where the system has a way to ensure that it does not encounter an unsafe state during the first I moves. Okay, and we'll kind of incrementally build these sets, as we increase I, right? So essentially, if you look at X0 is essentially saying that you should be starting at a safe state, right? So that's very clear. You just remove the unsafe state, and X0 contains all these three states, right? Now you remove a state from X0, right? If environment has an option of picking a letter which is available at that state, and no matter which outgoing edge I choose on that state, all of them take me outside X0, right? So for instance, if I'm at S4 and the environment plays C, then I'm going to enter this unsafe state S3. Right, so therefore S4 needs to be removed from X0. So X1 is obtained essentially by removing S4 from the current X0, which is these three states. And you keep on doing this, this sort of a calculation, right? And this calculation definitely reaches a fixed point. That's what you call X. So this X is sort of what is called as a trap for the system play, right? Because this set of states has the property that every state which is inside this set, right, every letter which is enabled at such a state also has a successor inside this set, right? So this set is kind of closed under available letters, which are there at those states, right? So essentially the system has a way to ensure that it can, no matter what environment does, it will just remain inside that set. And because that set does not contain any unsafe state, this is in some sense the winning region for the system. Okay, so it's a very simple computation, and of course it can be carried out in a quadratic time. Right, and inside this region, system has a strategy to ensure that an unsafe state never occurs. And in fact, it has a strategy which does this using zero memory. Right, so in some sense, for every state which is inside this final fixed point, on every letter there is a successor state which is inside this set. So we just commit to that successor state, and no matter how the token comes to this point, I'm always going to follow that edge and remain here. Right, so it's a strategy which does not need to remember how I arrived at the current state, right? No matter where the game began, whenever the token comes to this state, it's going to just move to one of the successor states which is inside the trap, which is guaranteed. Okay, so these strategies are very special because they can be very easily implemented, right? So we have, for safety games, we have these two nice features. The winning region can be computed in quadratic time, and it is whenever there is a strategy, there is a zero memory strategy. Okay, so now let me sort of take this as a starting point, Okay, and let's sort of look at an asynchronous version of this situation. Okay, so let's look at let's introduce one more process into the system. Okay, so now we have a safety game where there are two processes. Okay, and yeah, so there are so you should really think of these these two processes as sort of cooperating with each other. They want to beat this environment, right, which is an adversarial component here, right? And so these two processes have their own individual NFAs. Okay, and the idea is that these individual NFAs, so the basically the input, right, to this asynchronous system, every letter has been classified as one of these three letters. Okay, so every letter is either local to the first process. Okay, so that means that only the first NFA is going to react to that letter. Right, that letter will not even be seen in some sense by the second NFA. Right, there are letters which are purely local to the second NFA. So only second NFA is going to see those letters. First NFA will not even come to know whether those letters are seen there or not. And there are these synchronizing letters where both these NFAs come together. Right, they are in some states, they see this common shared letter and they react to it, and then they sort of advance their states. Okay, so there are these joint letters and local letters. Right, and the sort of you begin in an initial global state, right, and you have a notion of unsafe global states. Okay, so you have this sort of we have taken this safety game on an NFA and sort of generalized it to this asynchronous setting where there are two processes. Okay, and we'll sort of look at this question. Okay, so just as a concrete example, right, so in these two pictures you see that the letter C is purely local to this NFA of process 1, the left process is process 1, and the letter D is purely local to the NFA of process 2, right? And A and B are these common letters, right? So the understanding is that, when you are at a current global state, right, when a joint letter, the environment can schedule a joint letter, only both of them are willing to participate in that joint letter, right? So for instance, at Q0, R0, the letter A and letter B are both unable, right? Because there is an A transition in the left, sort of first NFA. There is also an A transition in the second NFA. Okay, so if the environment schedules an A, then this moves to A, this left NFA moves to Q1 and the right NFA moves to R1. They sort of synchronize and they simultaneously change their local states, right? They update their locals, right? But of course, the environment controls whether it's going to schedule A or B. Right, so it's in the right. It's the environment which decides, what to play, whether to play A or B. Right, so the letters are always controlled by the environment. Right, but some letters are joint and some letters are local. Okay, and of course, this initial state is a sort of is common knowledge. Both of them know where. Right, each process knows where the other process is starting. And let's say the global states are these. So red comma red is a bad combination, or blue comma blue is a bad combination, right? So the color matching is a bad combination. Let's see something like that. Okay, and let's look at a run of this, a distributed play of this mechanism. Okay, so they both, as I said, both start at Q0, R0, and let's say that this A is scheduled, the environment schedules an A, right? So both of them, the left NFA moves to Q1, the right NFA moves to R1, and this is where they are right? At this point, right, the environment can schedule C. Note that environment can also schedule D, right? These are purely local letters. And in this picture, so I have drawn these sort of, these horizontal lines are lifelines of the processes, right, as they evolve in time, right? So they started here. The first thing that happened was the synchronization A was scheduled. They moved here. Now the next thing that happens, which is what I'm calling event E2, the letter C is scheduled, okay? And then this NFA reacts by moving to Q2, and that's really the only option that it has. Right, on C. So it just moves to Q2. And let's say now, right, at this event E3, the letter D is scheduled, right? But note that because of this asynchronous nature and so on, the locality, right, when this D is scheduled, process 2 does not know that parallelly the letter C was scheduled, right? So in some sense, when you are talking about a distributed sort of phenomenon, right, these two events are actually concurrent, right, because they are happening at different sites, right? One event was scheduled on NFA1 parallelly, in some sense, if you like, another event was scheduled at TF, right? And while one event is scheduled at a local NFA, multiple events in a sequence might be scheduled at a parallel NFA and unbounded limit, right? That's why it's an asynchronous sort of system, right? So, so here this C happens, then this another C is scheduled, right? And then maybe you come here, and then another C is scheduled, and you come here, right? So this event E3 is concurrent with all these three events, E2, E4, and E. Right? While of course they happen, sort of in this order, right? So essentially, if you look at these sort of timing diagrams or process diagrams as to how the processes evolve over time, right? How they react to there is a very natural partial order on these events, right? What causes what to happen and so on and so on, right? So for example, right, in this partial order, you should see that E2, E4, E5, all of them are sort of concurrent with E3. Right, within them, of course, there is a total order between E2, E4, E5 because they are happening on the same process line. Right, so that's what is called as a trace. Here is another sort of computation, right? Another play of the same thing. What I want to highlight is that when we interpret the winning condition, right? So a play happens which should really be thought of as a partial order, labeled partial order, right? And you say that this is a winning play for the system, right? If an unsafe global state never occurs, right? And this is also valid unsafe global state, right? So this kind of a cut is also okay because these two events are really concurrent, right? There is no causality between these two events, right? They are really parallel. So they just that in time it came before this, but it could have very well happened later, right? So the notion of winning condition is to be interpreted at sort of, a set of events which is kind of downward close, right? Which is possible, which could have indeed arisen. Okay, so the winning condition is to be interpreted at the level of partial order, right? That's the natural interpretation. That's a synchronization letter, yes. Yeah. So each letter comes with sort of, its type. Each letter comes with a type as to whether it's a process 1 letter or process 2 letter, or it's a synchronizing letter, right? So in this example, A and B are synchronizing letters, and C and D are purely local letters. That's right. Yeah. So that is a static sort of thing. No, so I'm saying when you interpret the winning condition, you don't interpret only at these kind of, right? You also have to interpret at these cuts, right? These cuts are essentially possible causal histories which are possible, right? It's causally everything is consistent, right? So, right, what I mean by, yeah, all possible cuts, right. Okay, so as I said, a play can be thought of as a labeled partial order, and these are called so-called Mazurkiewicz traces. Okay, and so what is the distributed strategy in this setup, right? So we have seen the notion of a play and what sort of information is available to these processes. So the idea is that it's a sort of advice, distributed strategy is an advice that these processes follow to react to the letters that the environment produces, right? So we have to sort of provide the matching transitions. And while providing matching transitions, this must happen, that if it's a local action, right, which is local to a particular NFA, then only that process has to, of course, react. And it has this information, what is called as the causal past of that event, right? So what it is allowed to sort of observe is everything that happened until the last synchronization. So the last time it talked to the other NFA, everything before that is known to this process, right? But after that last synchronization, only the information, only the letters which were local letters which were played on that NFA, that information is available to this process, right? And it has to use only this information to decide the matching transition, right? So it's a completely partial information game in terms of games, right? Yeah. Oh my God. Okay. Okay, and while on joint actions, of course, they exchange causal paths and they're allowed to use that information. Okay, and we'll also talk about these distributed sort of strategy which use a finite amount of memory, in order to compute this advice. Okay, so here is the sort of problem statement now. Given this two-process safety game, you want to know, whether there is a distributed strategy, right? This sort of causal path-based reaction to the the letters provided by the environment, so that the safety condition is always met, right? The system never encounters an unsafe global state as long as it's following this advice, right? Whether such a strategy exists or not is the question that we want.
It's defined of the...
No, it's a global. So you have these global things, right? So for example, this is, so Q2, R2 dash is a unsafe thing, right? I don't want this component, I don't want this global state to occur, where this NFA1 is residing at Q2 and NFA2 is residing at R2 dash. That should never occur during a computation. So Q2 R2 is considered safe, right? So you declare which global states are unsafe, right? So that's part of the problem, right? So the problem specifies which global states are safe, and therefore it indirectly specifies which are unsafe. Okay, yeah. So one sort of feature or whatever is of these is that unlike these usual safety games on one process, right, where we always had this luxury of having a zero memory winning strategy, that sort of breaks down in this case. Okay, because it's the environment which decides, whether this NFA1 will be sent to the left side or right side, depending on, whether it schedules A or B, right? The choice of scheduling A or B is with the environment. So therefore, it can essentially control, whether this, this NFA will go left or right, right? And that information needs to be used here in order to avoid an unsafe state in the future. Okay, so that amount of memory, right? So in some sense, this NFA needs to remember, right, when it is an R1, whether the previous letter which was scheduled by the environment was an A or B. How did it come here? Did it come via A or did it come via B? And that information can be useful to decide, to go the right way so that an unsafe global state is avoided in the future. Okay, so this example illustrates that now you need some non-trivial memory in order to, have a distributed winning strategy, right?
But is this even, maybe you can increase the number of states and remember.
Correct. So, but then that's part of the additional memory, right? So in some sense, that's not part of the game structure, but you are blowing up the game structure by providing additional memory. That's how we think of additional memory. These are the inputs, right? So these structures, these NFAs are given to you as inputs, right? So, yeah. And we want to know whether, we need additional memory besides what is part of the input in order to win. Okay, so let me just quickly show you how, and I guess I'll probably have to end with this, but let's see. Okay, so so what we want to sort of do first is that we want to know whether there is a distributed winning strategy, okay, against this environment, right? But let's sort of restrict the environment to start with, okay? Let's say that the environment is sort of limited in the sense that it is not allowed to play any synchronization. Okay, so although the shared actions letters are available, we are going to say environment is prohibited from playing any of those joint synchronizations. All it can do is it can just produce these local letters, right? It can just make this NFA move and that NFA move. Okay, and that setting can be very easily solved, essentially based on this solution that we have for the one process case. Okay, so we had this notion of a trap, and we now just localize that notion of a trap to each of these individual processes. Okay, except that there is no notion of a local safety because the safety is at the level of global states. Okay, but we can still have this notion of a trap. So it's a subset of local states, right? So Xi is local states of a subset of local states for the ith NFA, which has this property that it is closed under successors on the local letters of that NFA. Okay, so that's a trap for this process 1. This is the trap for process 2, and a combination of these traps is what is called as a rectangle, right? So this set x1 cross x2 is a rectangle, right? And a rectangle is sort of said to be safe if every state inside this rectangle is a safe global state, right? So now states in the rectangle are global states, and if nowhere I see a unsafe global state in that rectangle, then the rectangle is safe. Okay, and one can sort of you can easily convince yourself that the winning region, right, under this restriction on the environment is essentially those safe rectangles, right? So the part of the unsafe global states which can be covered by safe rectangles, right? So you have these, you have the entire set of global states, right? Some global states are unsafe. You forget about them. Of course, there's no hope of winning there because you're starting at an unsafe global state, right? But if you are starting outside this, inside a safe global state, and if you are guaranteed that you have these pair of local traps, right, which produce a safe rectangle, so you are never going to move out of that rectangle, right? That kind of ensures that, you can just, will never see an unsafe global state, provided environment does not play any joint action, right? So this is the simple sort of, so it needs a little more argument, but essentially, this is the winning region against a limited environment, which does not schedule any joint actions, right? And now we need to worry about what happens when the environment schedules joint actions. And that we take care of by using a fixed point idea. But the fixed point now operates only on the number of joint actions that are scheduled by the environment. Okay, so you start with the sort of, the safe region, which is the complement of the safe. Then you look at the covering, you look at the safe rectangles, the part of this region which can be sort of covered by the safe rectangles, right? And then if you are at a safe rectangle, right, but there is a joint action which takes you to a place where there is no safe rectangle, right? Then there is no hope of sort of, right, being in this place, because if you are at this place, the environment will schedule this joint action, will take you to a place where there is no safe rectangle, and therefore it will be eventually kill you, right? In some sense, make you force a visit to an unsafe global state. So you kind of work with this fixed point, right? And you sort of, you essentially compute this set uj where you have a winning strategy against an environment which is restricted to play at most j joint action. Okay, and you incrementally work with this. So again, a simple computation. So what happens at the end of this process is that you have this region, the fixed point of this process, which has the following two nice properties. First of all, this entire region W can be covered by safe rectangles, right? And for every state inside this region, whenever there is a joint action, right, there is also a successor on that joint action within that region, right? So it's closed under, right? So these two operations, it can be tiled by safe rectangles, and successors on joint actions are also within the part that you are closed. Okay, and now given this property, you can easily construct a winning strategy, distributed winning strategy within this part, right? So if you start at some state, you start in some initial state, right? Inside this region, you have a safe rectangle. So these two processes just sort of, commit to the axis of these safe rectangles and keep moving there, right? The environment may of course want to schedule a joint action and might want to take them off the safe rectangle. But even if the environment does that, they just land up into another safe rectangle. They land to a position which also is part of a safe rectangle, right? So if you can sort of, for every global state, if you fix a choice of a safe rectangle, the moment a joint action is scheduled, you go to a different place and you choose a safe rectangle there, right? So all that this means is that essentially the following result, that if you have a yes instance of this game, okay, then not only there exists a finite state distributed memory winning strategy, there exists one where each process essentially needs to know, what was the global state after the last synchronization. Okay, at the last synchronization, where was I thrown off? At that point, I have fixed address of a rectangle, and these two players start following that rectangle in some sense. Okay, so you do need additional memory, but that additional memory is very limited, right? It is of this form. Okay, and thanks to this, one can kind of show that this, this problem is in NP, and one also has a sort of accompanying NP hardness argument, and that shows that this problem is NP complete. Okay, so this is sort of in contrast with what happens for safety games. How much time do I have? Oh my God. Okay, so I wanted to start with something. So maybe I'll just tell you what the model is. It's quite interesting. So far we looked at only these two, distributed system with two processes. Okay, but many sort of interesting systems have this nice property that there is a notion of a central decision maker. Okay, so all the decision making that happens, in some sense, there is this designated process, and it participates in all key decision making activities. Okay, many distributed systems have this flavor. Many client server architectures follow this. If you look at a version control system like SVN or GitHub, right? Each users are concurrently making those changes, but when they have to sort of update the master copy, they acquire a lock, right? And that lock can be thought of as a sort of central decision maker process, which ensures that things are sort of safe or whatever, right? Some integrity is maintained, right? Another interesting example is, which all of us know, is working of an organization, right? So there is a head, right? And the idea is that, of course, lots of subcommittees are formed, right? But the decision-making committees, head is a de facto member of all those decision-making committees, right? So the head is always present. All the key decisions are sort of taken in the presence of the head, right? But for purpose of efficiency or to sort of expedite work, you might create a subcommittee and you might ask them to find out some rules and things like that, right? So in some sense, they are not decision-making entities, but they are just collecting some relevant information. And the final decision will happen in the presence of the central decision maker. Okay, so we want to talk about these games, where there is this CDM process, the central decision maker process, right? And yeah, so formally, this is what a CDM game is, right? So there is no sort of we are allowing unboundedly many processes, of course, finite, fixed, right, known beforehand, right? But there is this guarantee that there is this designated process, which has the property that if the action is not deterministic, right? So in some sense, when the environment schedules this action, there is a decision to be made whether I should go this way or that way or that way, right? So if the action is not deterministic, right, then this process is always part of that action, is going to participate in this action, right? The other participants for that action, I mean, for different actions may be different, right? But this designated process L is always part of all those actions where there is a non-determinism to be resolved. Okay, so sort of, here is an example of that sort of a situation. But so maybe so how much time? There's some 3 minutes. So maybe I'll just, okay. Yeah, so oops, sorry. Okay, so yeah, I think I'm kind of, yeah, I'm really confused what, okay, but let me just at least tell you the results. I will, unfortunately, I won't be able to give you the details. Okay, but it turns out that these safety games, with this global safety winning condition on the CDM, in the CDM setting, they can be solved and sort of fairly efficiently. They're just EXP time complete. Okay, and moreover, there is also this nice, property that whenever there is a strategy, there is also a strategy which uses a very limited amount of memory. Okay, and the memory has a very nice explicit form. Right, in some sense, every process, right? So, of course, the central decision maker is the one which is going to decide, right? And what we are saying is that what is that the central decision maker needs to know? So, it needs to know not only where it is currently, it also needs to know the current state of affairs of everybody else in the system, right? The best global state that this central decision maker is aware of, right? So, in this distributed computation, right, different people, different agents or different processes have different information, right? So it's a partial information situation, right? And what we are saying is that, this memory complexity result is saying that on these yes instances, right, there's always a strategy where the CDM is going to base its decision based on the best global state, right, that it is aware of for the entire system, right? The best information, the latest information that it has about every other agent. And that information is sufficient enough for it to make the right decisions to ensure that safety is guaranteed, right? No matter what input is provided. Okay, so I think maybe I'll just stop with that. Okay, so maybe let me just say this. So a natural question is, what happens if you have multiple decision makers, right? So if you have, say, 2 decision makers, right? What that means is that in every action which is non-deterministic, which is not deterministic, right, where some decision, either this process participates or that process participates, right? So some decisions are taken in the presence of this process and some decisions are taken in the presence of this process, right? But one of these 2 processes is definitely involved in any decision making, right? If you want to talk about, a 2 decision sort of maker model, okay? And it turns out that the problem quickly becomes undecidable. So, and we of course, it's really thanks to Hugo Gimbert, who showed similar undecidable results for the asynchronous control games. We really use very nice ideas from that work to get to this undecidability. Yeah, so I think maybe with that I'll stop.
Thanks, Bharat, for the nice talk. So for me, the takeaway is that having 2 deans in the department is not a good idea. So time for questions.
Unless you ensure that both of them are present in all key decision making, then it's really one decision making.
Okay. Yeah.
So in the beginning, when you were talking about the church problem, you were talking about all processes, but when you switch to all possible phi, but when you switch to two processes, you only talk about safety games.
Correct,
Why is
yeah.
that?
So we have also results for parity games and things like that. For simplicity, I just focus on safety games.
But the general question is,
The general question, I think for CDM architecture, we know how to solve it, right? Where you have the general fee, which can be written down as a MSO formula, but now interpreted over these partial orders, right? Which is what these process diagrams are, right? So I think for the CDM case, we have this Buki-Landweber type result. We are still working out the details, but that seems to be there, yeah.
and
We have certainly done parity games and so on the CDM.
one more, when you have the definition of global versus local, what does it mean when you have more than two processes? That if two people know, but not all of them, is it global or is it local?
It's semi-global. So when you say global safety, you usually say, yeah, but like for in mutual exclusion, you always say that, no two processes are in the critical section at the same time.
Okay.
Right? But that kind of implies whatever, yeah. So it depends on what one wants to specify, but in a mutual exclusion situation, right, you essentially you rule out two processes which are using the critical resource at the same time, right? And that should happen for any two processes.
Okay.
Right. So
Okay.
so we look at global safety. We also look at these local reachability, global reachability, where they sort of simultaneously reach them. So there are these variants that also, those have also been studied. And we kind of understand what the decision complexity of those problems are and what are the memory complexities of those problems. So we sort of have a reasonable understanding for the two process case and the CDM case. But of course, a lot of interesting work remains to be done. There are many other three process settings, we really don't understand what sort of memory structures are needed to win three process games. They seem to be, they are decidable, I think, but we don't really understand what exactly the memory complexity of these games.
Okay, thank you.
Yeah.
Other questions? So, okay, I have a quick one. So
Yeah.
what about LTL objectives in general? Like if I give LTL specifications, then...
So for the CDM came because I'm, so of course, if you sort of trust me that the general FIs, the general MSO specification works, the LTL specification will also work, right? But LTL is now interpreted at the partial order, right? The
Yeah.
specification has to respect the concurrency.
Yeah, I mean
Right.
the complexity, like you were talking about for
that needs to be analyzed. Yeah.
I mean, you were saying that it's decidable, but the complexity exactly it's
Yeah. So the complexity theory theoretic analysis remains to be carried out. That's not.
Okay. Other questions? Okay. If not, then let's thank Bharat once again. So we have a small memento.
Okay, it's my time. So first of all, thank you for participating. I want to thank all the speakers, all the keynote speakers, and all the other speakers for this for their great thoughts and their participation. Yep. We have prizes for the best student presenters. We have three prizes given by each of the keynote speakers. And I was told to mention that all the talks were quote unquote excellent and they were genuinely enjoyed. It's a quote unquote. So I would like to call Jatin to give the awards. So I didn't want to say 1, 2, and 3. So I named them. The Max Fleet Award would go to Sri Jato. Is he here? Max Fleet. Okay. The Max Independent Set Award goes to Malhar, who is here. The minimum vertex tower award goes to Yashwant, who is there's no award for that. So who is Srijato's best friend? Yeah, you should give it. Give it to Arkadev. Yeah, it's
Is it my time now?
yeah. Okay, thank you, Jatin. Huh? It's not recorded. Okay. It's not recorded. I will delete it. Okay, I would also want to especially thank the keynote speakers for coming all the way and giving great talks without any quotes. So I would like to thank Chiranjeev Bhattacharya, Neil Dhara Mishra, and Bharat Adsul for their great talks. Next, I want to thank the session chairs. We had 5 student chairs who chaired sessions amazingly. So let's thank all of them. They are Soham, Nishant, Spandan, Soumyadeep, and Andrila. I would also like to thank Ram Prasad, Shivashish, and Vinod for introducing the keynote speakers, and Kavita for her opening remarks. And I would also want to thank Jatin for helping me organize the symposium. He's actually the chief organizer who let me be here. Okay. Despite being the organizers, most of my job was sending emails to delegate things to different people. I was able to find the right people for the right jobs. And the actual jobs are done by our department staff, including, which is Sana, Sakshi, Vaman, Nitin, and Ravi. They handled everything from the website to the Zoom and YouTube links to the posters to the gifts, inviting the speakers, coordinating their arrangements, having these prizes, having these honorariums and flights and bookings, everything. So let's give them a big round of applause. There are also several other teams that helped us in this event. I would just list the teams and the names, and we can thank them. So the AV team consisting of Amish Kumar Pandya, Manjappa Hosakeri, Pandurant Soya, Labad, and Gaurav Avasthi, and Nitin from our department. The photography team with Jatin Acharya and Vijay Shinde. CCCF, which is, it has something to do with computing, I don't remember, but some CCC as one of the C's is computing. Consisting of Vineet Bhosle, Swapnil Malwankar, and Vinod Lad. The accounts group with Natwa, Manisha Rele, Nitin Hanjankar, and Kishore Pathankar. The transport group, the canteen staff consisting of Avinash Tambe, Rakesh Katkar, Nikita Aire, and Jadhav, sir. The purchase group consisting of Suchita Atre, Kalpana Matre, and Harshad Bhilare. The other teams that helped us include the store group, the external dinner venue, Global Fusion, the accommodation at Ramanujan, Jagdish, and Panini, the cosmetic arrangements, the security department, the gardening group, the archives group. So let us thank all of them, and someone I may have forgotten to mention, if any. So after the thanks, it's time to welcome. And I would like to take this opportunity to welcome all the first-year students. We have 7 great students this year, so let's welcome them to our group. And yeah, that's all. For our friends from IITB, thank you for coming. If you want money, then give your taxi receipts. Okay, thank you all. Thanks.
We should also thank the audience, people who didn't give talk, who were not keynote speakers, who were not. So thanks a lot to the IIT Bombay. All the way in this day.
We should also thank Indra Verma.
Special thanks for the AIT to keep the streaming going.
Thanks for coming.